Hi, everyone. Thanks for tuning in. I'm Ian, for those who don't know me, and welcome to GDG Zagreb Meetup. And today we have two guests. First will be our local Google developer expert for Android and Kotlin, and maybe Flutter soon, Filip. Philip will introduce himself later. He'll be talking about Kotlin Flow, the latest addition to the Kotlin library. And after that, we'll have Shaun Thomas. He'll be tuning in from Dallas to speak about Kodein, the dependency injector or service locator library for Kotlin. So, Philip, I'm leaving it all to you.
Awesome. Let me just share my screen a bit. Can you see, I guess, yourself and then the Flow presentation?
Yeah.
Okay, awesome. Okay, so thank you, Ian, for introducing me or giving me this opportunity to introduce myself. As he mentioned, my name is Filip Babić. I'm currently living in Osijek, and I do a lot of community work. I do a lot of public speaking engagements. I write tutorials, articles, blogs, even books sometimes for Raven Relic, and this kind of resulted in me becoming a GD for Android and Kotlin. So I'm really happy to be able to talk about Flow, an API which I haven't really used that much, but I guess I'll be able to share some of the things I know about it and how it works behind the scenes. And for those of you who may not know, Flow is a call stream API from JetBrains, which is powered by Kotlin coroutines. So it's meant to represent a streaming API, which can also benefit from all the things that coroutines provide, such as cancellation, using suspending functions, and trying to suspend the consumer or the producer in a way to create either back pressure or just delay some work. So some of the things I'll be covering are coroutines in general. So of course, because Flow is powered by coroutines, I have to mention coroutines. And I guess that it's one of those buzzwords today. And even though it's a buzzword, some people may not really know what coroutines are and how they work behind the scenes. I'll talk about the async problems or problems in the async world. So some of the things that we may see when we're working with an async API. Also, the legacy of Rx, or why Rx and similar mechanisms are now being replaced, or at least Flow is trying to replace or maybe give a new way of dealing with asynchronous streams, which may eventually replace or fill a new gap that Rx doesn't. And then I'll talk about the flows and its specifics. So once again, let's talk about coroutines and what they are, how they work. Coroutines are, it's actually a pretty simple concept when you think about it, because it's a low level mechanism, and it's actually just based on low level scheduling. So it's an old concept which gives you an ability to schedule between threads and or schedule work, which will then switch between threads, and also synchronize threads without having to add more overhead to your code, or even make you do more manual work. So it allows you to synchronize between threads easily, and it does so through the concepts of suspending and resuming, and we'll see what that is in a bit. So some of the important parts of coroutines and the coroutines API in general are the coroutine context, the coroutine scope, and the suspend modifiers. The scope is kind of the bread and butter, and it's sort of the baseline of every coroutine, because that's what you usually start with. A coroutine scope is a lifecycle element of the coroutine, so to say. So it's a way to bind coroutines to a certain lifecycle, and then you can dictate the lifecycle of the coroutine through that scope. So think of it like this way: if you are working in Android or any other lifecycle-based applications, where you clearly know when your app starts or finishes, or you clearly know where when in code some of the components start or finish, then you use a coroutine scope to attach coroutines to that lifecycle. And what that does in return is you can freely cancel all the coroutines within that scope, and you can start coroutines when you know your components are ready. So for example, if you're trying to fetch some data when the fragment has started or the activity has started, you can just start a bunch of coroutines within a scope, and if that fragment is killed, or that activity is killed, you can just cancel those coroutines, and the resources will be cleaned up. The coroutine context, on the other hand, is a set of elements which describes the rules the coroutines have to follow. So if you have that coroutine scope and you want your coroutines to run on the main thread, one of the coroutine context elements may be the threading mechanism, which is the dispatcher, which will give you the ability to say, okay, when I run coroutines in this scope, I want it to run on the main thread. Another element might be the exception handling element, which will simply say, okay, if an exception occurs, this is what's going to happen. And the third element will be the lifecycle, and that's kind of hidden behind a job construct, which is like a special object. And the job is basically like a piece of work wrapped in an object, which you can then use to cancel that piece of work. So all that combined creates a coroutine context, and similar to how the context in Android works, it's a way to describe your surroundings and the environment of things you want to run coroutines in. So as I mentioned, it can be threading, it can be exception handling, or the lifecycle of the coroutine. You don't have to combine all three, but you can combine any number of them. And finally, this suspending mechanism of coroutines, or the suspending functions. Currently, it's a suspend modifier, which is just like a modifier, which says if you call this function, it might be suspended, or it might suspend, actually. So what that means is you won't block any threads, so to say, or at least you won't block the thread you run the coroutine in. So when you suspend a function or call a suspending function, it suspends its parent and says, okay, while I'm working, you should wait, and once the work is finished, once I'm ready to proceed on with the code, if I return a value or something like that, then you can come back and take that value and continue with your work. So that's kind of what suspend does in this context. So to picture it in a way is, let's say we have a main thread which we're running a function which is called getUser, and let's say that getUser function is a blocking call. This will in turn block the main thread, and only after getUser is finished, we'll get back the main thread. It will free up, and we'll be able to update the UI. After which the function will end in general. So that's kind of our life cycle of things. Now, what happens if you use coroutines is that, or let's say, what happens if you want to do two things in parallel? You want to call getUser, but you also want to update a different part of the view. If getUser is blocking, the main thread will be blocked, and only after the getUser function is finished and you proceed to update the UI, will you be able to update the view as well, which is like a separate function. So you can't do two things in parallel because the main thread is being blocked by the one operation, and it can't proceed with the other one. But if you use coroutines, what happens is if you call getUser within the main thread powered coroutine, and it's a suspend function, so it has the suspend modifier or uses another suspend function, it will actually suspend the main thread coroutine, which will mean that the coroutine will kind of sleep, so to say, and the main thread will be freed, which means that you can run other functions such as update UI, which can be on a coroutine or doesn't have to be. And only after the getUser function is finished will you be able to, or let's say it like this, after the getUser function is finished, it will call back to the main thread coroutine using like a low-level callback. It will say, hey, this value is computed, and now you can call the update view function. So that will trigger the main thread coroutine again, awake it, so to say, and you'll be able to call the update view function or update UI function, whatever you want to call it. So you'll be able to run two things in parallel, so to say, because you can call one function, let the main thread run other work while you're calling it, but it will still have that sequential syntax, and you won't have to worry about manual thread synchronization or anything like that. So that's kind of what a coroutine does and what the API is about. And when we think about the async world and async programming in general, Async is really hard because it has a lot of problems because we are kind of human, so to say. Because asynchronous programming is not really intuitive to humans. We're all sequential. When we pick up the phone and we talk on a phone, even though people say we can multitask, if you can't really listen to the person and run a steady and healthy conversation if you're trying to type something else on a laptop, or you're trying to watch a TV show or something else completely. So we kind of think in that way, that we're doing one task at a time, and only once that task is finished, we can fully commit to another task. So thread switching and synchronization can be really hard, not just in code to do manually, but also it's hard for humans to understand. So if you look at that, having one value is very complicated, but having multiple values is even harder. If you can't really fathom the fact that you have to fetch one value from another thread, synchronize those threads, and then asynchronously update your UI or whatever you want to do, how are you supposed to think about fetching multiple values, and maybe even doing that over time? That's even more complex. So we can think about it in a few ways if you're working with code structures, or just if you're thinking of a programming way how to do it. You can create like a hot dynamic list, which is initially empty. It's a mutable list, so you can make it public and share between threads, which kind of means that any thread can update it, add or remove items, and it can manually refresh that list. Meaning that you can have race conditions, you can have states where you accidentally updated the list, but you forgot to remove an item, and then another component reuses the same item which you already consumed. So it's very prone to mutability, issues, which is race conditions, and just in general, not having the structure updated, or finding the single source of truth. You could use a sequence to produce multiple values, and you can give it a way to produce value each time you try to consume a new value. It can be cold, it can be lazy, so it doesn't have to be hot, and it doesn't have to take up memory immediately. But it also can be memory intensive, because if you're trying to fetch 10 values from the list every second, you effectively have to cache those 10 values in the sequence and produce those 10 values. You can't just say, hey, I want the last value, unless if you're not computing all the previous ones, or at least that's kind of the basis of sequences. Of course, you can do it in different ways and hacky ways, possibly, but it's also very hard to think about it, and very hard to actually program which in a way that it's optimized and just works out of the box. So with coroutines, we have this first approach where we just say, okay, I want to launch a coroutine, I want to fetch something from the background thread, and then show that data on the main thread. And that's pretty much what happens here. That's pretty much what you write, and it's very intuitive. But you can't really do that the same with lists or sequences, because you can launch on the main thread, produce something in the background, but how do you keep up with the list or the sequence, and how do you keep up with all the memory concerns behind that, and also race conditions? And you can also consider those values on the main thread, but if you use for each or something like that, you're essentially doing it in a sequential way, and you're not allowing the main thread to free up and do other work if you have a lot of values. So for these kinds of things, we usually use the observable pattern, where we, Rx is always mentioned here. So things like observables or flowables from the Rx, so Rx API or reactive extensions, whatever you want to call it. This is a very common pattern where we have one producer, which usually one producer, which gives you some values over time. It can have its own thread, own scheduler, or own thread pool, and it produces values in any way you write it. And it also has a lot of operators to transform those values, buffer them, delay them, filter them, and stuff like that. So That's one side of the thing, and the consumer is the other side of the coin, which turns that call structure, that declarative, stream of events into an actual stream of data where values are being produced, and you get to consume them. And you observe those changes, you offload work from the main thread, and that's all fine. But these kinds of things also have a lot of problems, because the learning curve can be really, really steep. When you look at Rx, it's not just a matter of knowing how the operators work in a way, how a map operator works or a flat map operator works in terms of mathematical transformation. So flat map flattening the structure, and map just taking each element and transforming it into something else. It's not just based on the lambda functions which are supposed to transform those values. A lot of operators also have different threading capabilities, and these threading, thread switching options and just different behavior for threads relies on the operators you are using. So a lot more problems can come from that, because you may not know how the threading will change if you use a special operator. But that operator might just fix your problem, or might create the use case you need. But it might also create a lot of other problems you may not be aware of in first. So that's one of these kind of issues that these complex libraries have. And in the end, these are third-party libraries. So if something new comes up in Android or the JVM, or in general the programming world, someone has to update those libraries, and someone has to make sure there are no bugs, no errors. That they have to fix everything in a way that it's also backwards compatible, but in a way that it's understandable to both new and older people, or people who have been already using the library. So it's not a part of the language specification, and because of that, you can't really rely on the same team constantly updating the API as they update the language. And because of this, we kind of have the Kotlin Flow library come in. It's Kotlin's way of dealing with async streams of values. And that being said, it's built in into the Kotlin's library, so to say, in a way that is being developed by the same team. Of course, it's open source, so you can contribute to it yourself. But in general, there's a team working at the Kotlin language, at the compiler, at the coroutines part of the API, and also the compiler behind the coroutines, and the Flow API. So it's all kind of going neck to neck, and as the language is being updated, so are these libraries. So you don't have to worry about Flow falling behind the language or something like that. So it's kind of supposed to all work together. And because it's a part of the language and part of the language specification, you can be sure that it kind of works with all the new features of the language, and that it's being developed in a good way by the same people that are developing the language you're using. So what is Flow, and how does it create a new solution to async problems? First off, it's a way to create streams of values, called streams of values, powered by Kotlin coroutines. And I'll get to what this means a bit later on. Secondly, it's a very simple API, to be honest. It has only two interfaces. It has the Flow interface, which is the general what you want to consume, and the Flow collector, which is kind of the consumer side of things, where you say, I want to collect these values in this way or that way. So the Flow represents the producer side of things, the actual stream, which is called, and the collector represents the consumer's call side of things, where you get to consume those values. And that being said, and Flow being powered by coroutines means that you always have to use coroutines or wrap your Flow usage within the Kotlin coroutines API. And I'll also mention how this helps out a bit later on. So this is kind of the Flow API overall. Let's say you have the Flow interface, which is generic, and it has one function which says collect, and it can collect by receiving a Flow collector to which it will send all the values it emits. The collector, on the other hand, has a single value, or like a single function, or a single main function at least, which is emit, which basically sends a value and of any type, and then updates the flow. So when you use a flow, you generally say, okay, I want to create a flow of the following values. You don't have to emit any values within the flow, but as soon as you call emit, it being a suspend function will suspend the actual flow, the actual emitter side of things, the producer side of things, until that value has been sent. Which means that if this value is like a hard to produce value, it's an expensive operation, it will effectively suspend the flow until that operation is done. So if you have operations which you have to run multiple times, but they are really long, you won't receive any back pressure problems or buffering problems or blocking issues regarding threads, because you essentially suspend the flow, releasing its thread. You produce a value, and then once it's ready, you send the value or the event through that flow. So you don't have to worry about blocking the flow or blocking a thread with your operations. And then when you want to consume the flow, all you have to do is wrap it within a coroutine or another suspending function. So in this case, we wrap it within a launch block. We say we want to use that flow. We want to map each value to produce its length, for example, and then we want to collect. Now, the important thing here is to notice the launch block. So as I mentioned before, when you create a coroutine on a coroutine scope, it has this job behind the scenes, which it uses to represent its lifecycle. And if you cancel that scope, or if you clear that scope, which is kind of similar to disposing of observables or like subscriptions within Rx, you cancel that coroutine, in turn canceling the flow collection. So you don't have to worry about any values being consumed after you try to cancel it, or you don't have to worry about any memory leak. So it's a real nice way of doing things. You can also do something similar to this, where you transform one type of collection or sequence or range to a flow. So if you have like a fixed set of items in a range, for example, you can just say as flow, or you can do the same on like collections or sequences, and it will turn that iterable sequence into a flow, which means that if you try to collect it, it will behave just as another flow, but it will also have like predefined elements. So you don't have to worry about producing those elements beforehand. Now, Flow has two main types of operators. The first are intermediate operators, and they basically take an upstream flow. So basically, any flow which any current flow state or any current flow construct, they apply some transformation and return a downstream flow. A downstream flow is basically any flow you actually want to consume or you want to further transform. So the upstream is basically the source, and the more upstream you go, the more you get to the source. And the downstream is the end product you want to consume. So these operators usually tie into two smaller categories, which are transform operators or size limiting operators. So you can just use transform, which takes each value and transforms it in any way you want. You can use map to map from one type to another. You can use filter to filter some of the values according to some condition, which are all transform operators. And you also have size limiting operators such as take or single or first. So where you say I want only the first value or something like that. So you just on the first 5 values. So you limit the size of the flow in a way. And as I mentioned, these are also kind of terminal operators too, when you want to just take one or few values. Terminal operators are operators which finalize the flow. So they turn it into an active structure, which is like an active stream, or an actual value. The simplest one is the collect operator, where you say, I want to collect these values, and that's pretty much it. You collect it in any way you want. It turns a cold structure, a cold stream, into an actual active structure which emits values. The other way to terminate the flow, so to say, is to transform it into another collection. such as using to list or to set, or any other number of operations which you can use to turn them into some kind of collection. And also, these are also kind of in both intermediate and terminal operators where you want to take the first or single value, but you can also reduce the entire flow or fold them into a single value. If you have a flow of integers, you can just reduce them into one integer, which will be the sum of it, or you can multiply all the values or something like that. These are the operators, but there are plenty of operators out there, and just like with Rx, you can pretty much do anything with a flow. You can partition it, you can filter it, you can transform it into different ways, you can take only a certain number of items, you can only you can pretty much do anything you want with it. If you don't have an operator for a flow, you can just write your own, because compared to Rx and all the intricacies behind Rx, flow operators are generally naive Kotlin code, which doesn't really involve a lot of complex threading or switching between objects and stuff like that. You can just say, okay, I want to merge these two flows by taking all the values from the first one, from the second one, and then emitting them all into a third flow, which is like the resulting flow. But one thing that flow has, which kind of differentiates it from other structures, is that it has a few rules to follow. And these rules are context preservation and exception transparency. The context preservation basically means that as you work with a flow, when you call collect on flow and when you try to collect values, you have to preserve the context of that flow, or of that parent, to be exact. So what this means is you can't really say, like in Rx you would, you can say any number of times I want to switch the dispatcher from the what you call it. So you say observe on and what's the other one? I'm not entirely sure. I can't really remember. But basically, you can observe on one dispatcher and switch it any number of times you want. And there's an intricacy between when you call observe on and schedule on, I think, and what the order is and stuff like that. In Flow, you can change the upstream flow thread or dispatcher, whatever you want to call it, any number of times, but the end result, the collection of flow, always happens on the context of the parent coroutine you collect on. So what this means is when you call collect on a main thread dispatcher, or within a coroutine which has a main thread dispatcher, you will essentially collect on the main thread. You can't switch that any way you want. If you try to do so, it will crash. So it will give you an exception saying you have to preserve the context. And this is a nice way of dealing with things, because you don't have to worry about creating some crazy context switches, or maybe even creating some crazy use cases where you accidentally switch the context and now you get a bad result or like a bad behavior. And by having this preservation rule, you always know where your collection is going to happen, so you don't have to think about it. The other rule is the exception transparency rule. And this basically means that within flows, you shouldn't really use try-catch blocks. You should always try to let those exceptions happen if they happen. But if you want to catch them and deal with them, you have to use the catch operator. So basically, what you're trying to do here is you're not trying to let any exceptions disappear or get unhandled. You want to let them happen and then let the consumer handle those exceptions in any way they want. So, So regarding context preservation, you can always use flow on to switch the context of the upstream flow. So once you call flow on, all the upstream operators will be switched. But once you call collect, it will look at the context of the parent and mark it as the consuming context, so to say. And you can switch that context anyway. And if you do try to do that, you will get an exception. So let's kind of look at an example here. Once again, we try to produce like a basic flow, which is a flow of 10 values, integers being turned into strings. And you say at the end, you want this flow to flow on some dispatcher. meaning you want it to be executed on, let's say, dispatcher's IO. And that's fine. Everything from above that flow on call will be move on to the dispatcher's IO, which is basically just the flow here. If once we try to work something with that flow, once we call the map operator, it will kind of default to a different dispatcher. So you also have to change that up to the same dispatcher if you want to do some extra logic. So what happens here is there won't be two thread switches or two context switches. The flow operator will know that just like in a sequence, when it looks downstream and it does all the operators kind of in parallel, or let's say at the same time. Here it looks at all the dispatchers and it knows which dispatchers is going to finally switch to. So in this case, it's the whatever dispatcher we pass in the second flow on call. So we can change the upstream context, but the actual collect is going to be preserved by the scopes or the launch blocks context. So if the scope is on the main thread, it will essentially run on the main thread. So in this way, you don't have to worry about switching back to the main thread, because if you're running some code or collecting on the main thread by default, you don't have to worry about that. And if you want to switch anything or any operation from flow to the IO dispatcher or like a default dispatcher, you can just do that using flow on. So it's a really easy way to switch context here, but it's also really safe, as you'll never switch context at a bad time, or you'll always collect on the parent context you're collecting the flow in. The other rule is the exception transparency rule, and basically says every exception should be sent downstream. You shouldn't really use try-catch blocks and hide those exceptions from the user. You should instead let those exceptions happen and then use the catch operator to handle those exceptions. Handling here means that you can pretty much do anything you want with them. You can just print out the stack trace. You can do some extra complex logic. But what you can also do is emit more values or default values and transform the flow into something different. So here we have a way to do this. So we say, let's launch a coroutine again. Let's observe, or let's say collect the flow within that launch block. But before that, we say, let's catch any exception. So you open the catch block and you get the exception as the it parameter. So like the parameter of the Lambda function. Within that catch, you can say emit all the values, and you can either switch to a different flow. You can switch to like a default list of items you want to send if you have more than one item, or you can just emit one item by calling emit instead of emit all. And what this does is basically you have internal error handling. You can do anything you want with the error, and you can process it in any way you want. But instead of breaking the flow apart and canceling the entire flow, you can re-emit new values and let the end product be like a default value or something you already have, or something you already loaded. So like a different flow or something else. So for example, if you're fetching something from like a socket or some way of remote APIs, and you decide to use flows because there are multiple values being emitted, you can do that, and you can say catch. And if you catch any exceptions, instead of saying let's just cancel this flow and show nothing, you can say emit all and then take some values from the database and automatically emit those locally cached values. So you don't have to switch to or like flat map to a different operator or a different flow or anything like that. You can just say emit all the values from a different flow. So it's a much easier way of dealing with things. And as I mentioned, this only affects the upstream flow. So if you have any other operators or any other logic you do after the catch block, you also have to call catch again. So it will only use the last block, obviously, but I think it will use the last block. But the idea is, you should call catch just before you call collect. So you are sure that every single operator and business logic piece is being covered, unless you specifically want to avoid covering exceptions from like a function call or like a specific operator. So that kind of depends on your use case. So to sum it up, to show you the flow of things, Flows are call streams powered by Kotlin coroutines, which means that if you want to apply back pressure, you can just suspend the producer. If you can't process enough values in a small period of time, you can say, I want to suspend the consumer, or let's say, suspend the producer until the consumer is ready. Or the other way around, you can say, if the consumer is eagerly waiting for more values, but you can't produce enough, you can say, I want to suspend the producer, or once again, I want to suspend the consumer until the producer produces enough values. So you can go either way around, and you can just, keep back pressure just to simple either delay calls or just simple other suspending function calls. Every flow has to preserve its context, and it should be transparent with their exceptions. So you shouldn't really hide any try-catch blocks. You should just let the exceptions happen and catch any exceptions before collecting, and then maybe re-emitting some values after processing that exception. Flows have this cool compatibility with Rx, live data, room, and other different things where you can simply switch from one construct to another. There's a bunch of small libraries which do that for you. for you. So you don't have to worry about completely rewriting your Rx code or live data code or something else to introduce Flow. You can just introduce Flow like a middleman, just like you did with coroutines and retrofit or room or something like that. So yeah, there's specific support for Android. There's specific support for other third-party libraries, and there's a lot of cool new things happening lately, such as the state flow coming out, which is basically like a live data flow. It doesn't use live data behind the scenes, but you can both consume the values and also fetch the currently cached value, which is like a really cool thing. There's also a special issue, or whatever you want to call it, which is around broadcasting flows. So currently flows can't really broadcast. They can't fan out. You can do something similar by transforming it into a broadcast channel and then broadcasting that value to all the recipients or consumers. But there's been some work on a broadcast flow, which will, I think, in maybe a couple of weeks, maybe a couple of months, come out, and that will also solve that problem, which it currently doesn't support. So some of the common questions you might have around Flow are, how do you cancel a flow? And in general, you don't really cancel flows. You collect flows within a coroutine. So all you have to do is cancel that coroutine. The flow and everything will automatically be cleaned up because the coroutine has been canceled. And since the flow works within a coroutine, if there is no coroutine or if it gets canceled, it will automatically be cleaned up as well. So you don't have to worry about canceling your flow. You just cancel the coroutine. The other thing, people might ask, I'm used to switching to the background and then switching back to the main thread with maybe Rx or some other construct. So how do you do that in Flow? Well, once again, you don't have to. You can just launch your coroutine using the view model scope or the lifecycle scope, which are main thread first. And once you collect those values, they will be on the main thread. You don't have to switch back to the main thread, as it's done automatically for you. Another common question might be, is Flow blocking? Because it has this coroutine support, so is it blocking or suspending or something like that? And once again, it depends on what you write, but generally, if you write blocking functions to produce values within a flow, yes, it will be blocking within the thread that's producing the flow, but it won't be blocking within the thread that's collecting the flow. So once you get that value, you can just consume it and then move on. So you don't really block the main thread by producing values in a really long-running operation. And something I already kind of answered, how do you apply back pressure? Well, you simply suspend your consumer or your producer in any way you want. So you can do that with like a small suspend function, which produces a value, or you can do that by calling delay and delaying either the emission of the new event or new events, or the consuming of the event. So after you consume the event, you can delay for, let's say, half a second before getting new values. There are also like delay operators and debounce operators and conflate operators, stuff like that, where you kind of don't want to consume all the events you get, but only like a small set of events. And with that being said, are there any questions? And thank you, I guess.
Well, thank you. There doesn't seem to be any questions yet. But looking at it, I've been using Kotlin Flow for the last few months, and it really seems way better than RxJava. It's more performant. The APIs are way cleaner. And they recently introduced stuff like state flow, so you can create Redux so you don't have to make like channels yourself and keep the state yourself and replay it. Yeah, I think everyone should be replacing it. Yeah, if you're using Kotlin, yeah, dump RxJava.
Yeah, that's one of the things that I kind of saw, when the flow was in its initial works, there weren't as many. Oh, hey.
The other Ian. With better beard than me.
Working on it.
Yeah, as I was saying, there weren't as many operators in the beginnings of Flow. And what people said, if you need another operator, just write it yourself. Because it was that easy, it was just pure Kotlin. And you didn't have to write some complex things like you would in Rx, for example, with observables and special threading, the scheduler. So you can just write your own merge operator or filter or flatten, whatever you wanna do with the flow, because it's all Kotlin and you can use the extension functions and everything. So it really does create a clean API in the end.
Yeah, I agree. What's up with you, Ian?
Not much. Just gonna talk about coding.
How's life in Dallas?
It's back to being hot. It's not too hot today, but it keeps swinging between like 70 and 90 something. So
feels like somewhere. So could you introduce yourself for our audience?
Yeah.
Mostly Zagreb.
My name's Ian Thomas. I live in Dallas now. I was in the Orlando area for a while. I used to run the Android Meetup there, and I used to help the GDG event out in Florida for a while, and even spoke at the conference. So it's nice to join in on an international level now. I work for a company called PowerDMS, and I'm a lead for effectively our mobile team and kind of branching out a little bit to do some back-end stuff currently. So unfortunately, not really mobile dev anymore, I guess.
I gotta say, you got a pretty impressive collection back there.
Yeah,
Millennium Falcon and H Fighter.
There's a couple cars, I guess, on my left, and then on the right is like the space side, and a Millennium Falcon slipped in there on the bottom. So, but mostly NASA space stuff.
Nice.
Typical nerd.
Nice. So we're gonna leave the floor to you.
Yeah. Hopefully this is the right one. Looks like it. Great. Okay. So cracking Kodein. Kodein is a dependency injection tool. That's a Kraken, and it has nothing to do with the rest of this talk. So what is dependency injection? Dependency injection is just a way to solve inversion of control, right? You have instances of objects, and you give them to other objects that might need to operate on those instances. So one of the most basic and fundamental features of object-oriented programming. So a DI framework is just a tool to allow you to define these dependencies in a way that is more manageable and open to be extended and reused, possibly even in libraries and situations like that. But fundamentally in your apps, you're usually using them for managing your runtime dependencies that you've defined yourself and that are pertinent to your application. And only sometimes do they come from libraries, unless they're your own internal libraries. So Kodein is a way to enable you to do that and also provide those dependencies to other developers. So how do they usually work? Typically, it's a graph. So you define your bindings, and these bindings stack together and some kind of graph form. Obviously, the most common would just be like a flat map of these dependencies. But certain frameworks like Kodein support a little bit more complicated graph implementation where you can actually stack down a bit, and you can use things like overrides. But generally, they are just, if you can think of a hash map, you want some value, and the map can go get it for you in a graph kind of fashion. So when you use a DI framework, it's usually because you're building an application that's a little bit bigger than a hello world application. When you start working in a larger team, it becomes very difficult to manage these complex dependency chains. So while DI frameworks are inherently not something that anybody needs, they save a lot of time in providing features that you do commonly need. So if you can think about in Android, we have quite a few managers that provide system level features. These features, often you only want a single instance. So if you think about like notification manager, you don't really want 8 instances of notification manager, because when you go ask for the notification manager for the system, just one is enough. There's no reason to try to ask the system multiple times for the same notification manager. And a lot of other instances that are going to come up like that in your own code, if you can think about connecting to a database or connecting to HTTP web services, there's going to be a lot of instances where you either want singletons or you want provided instances, meaning that every time you ask, you want a new one, or maybe you want to attach certain key values to represent certain instances. So give me an HTTP client that's configured for talking to Google versus one that's configured to talking to YouTube. These would be examples of where the dependencies start getting complicated, and it's certainly something you could solve yourself in your own application code, but it's not necessarily something that you should be solving because other people have already done it for us. So in the context of coding and general dependency injection frameworks, what kind of things can you inject and what should you be injecting? Common examples are the managers, presenters, any kind of abstractions. So if you can think of, again, your data models, any kind of business logic, these are all things that are great for injection. And they also probably represent things that need dependencies on other features of your application software as well. So common DI frameworks. There's quite a few that you've probably heard of. Spring and Dagger are probably the most commonly known in the Java world. Dagger's obviously really only popular for Android developers, but other ones that pop up are Kodein, which is another new one, came out about the same time as Kodein, and I have Pico Container on my list and Juice. So those are all examples of dependency injection frameworks. More or less, some will argue the definition of it a little bit, but in general, those are quality examples that you can look towards of what other people see as dependency injection and how it should work. So from an Android developer's perspective, I'm going to imagine that most people use Dagger, and their experience, it probably works fine. And you're correct. Dagger and Dagger 2 do work fine. They are trying to solve a specific goal, and I would argue personally that they do solve that goal. However, in my experience, I've seen a lot of issues pop up through using Dagger. Defining bindings can be confusing. Their guide for Dagger is a bit lacking, and the typical example with the thermosiphon is beaten to death, and nobody knows what that is anyways, which if you've ever seen a dependency injection talk, this is always the first thing to get bashed on. A better, more concise guide would be really helpful for Dagger, and it just doesn't really have that, or at least last time I checked. Its documentation, on the other hand, is pretty good. However, the guide is not so good. So while you can figure out how to use individual pieces, they don't really convey much towards how to use it in your application as like a total project, right? You have to do that research yourself, which introduces a lot of learning. And that's where producers and modules can be confusing to use, because you're not necessarily sure how to use them or when to use them until you become more of an expert at Dagger, which is an unfortunate side effect. And because of that difficulty, what happens, again, in my experience, what I've seen a lot is that we end up with just a giant God module. And Dagger is just implemented in just one. There's like one file with 100 definitions in it, which kind of defeats the whole point of using the framework. You're kind of throwing away a lot of its value at that point. And everybody knows from a startup perspective that this can be painful for your application, creating a lot of overhead in that initialization step when the user first opens the app. And then lastly, again, this is kind of a personal opinion, but the compilation errors of Dagger are difficult to understand. And that is probably a good thing to call out right here, is that there is a difference in dependency injection frameworks being runtime versus compile time. And Dagger is a compile time dependency injection framework, whereas Kodein and others are runtime frameworks. And as I mentioned, the documentation is not comprehensive. The documentation on the code is comprehensive. The guides for how to use the code are where it's lacking most, in my opinion. And then the last note was that while Dagger is great, it is very limited in the types of injection that you can do and how those bindings are defined, which we'll get into that shortly. So Kodein. Kodein is a very simple yet useful dependency retrieval container, which is the technical definition. And that's where I was mentioning before that dependency injection frameworks is kind of a vague term. And you'll see a lot of arguments online of exactly what to call a certain dependency injection framework. It's kind of, it doesn't really matter too much as long as you get the thing that you're looking for. You need to define definitions for your application's features, and you need to be able to inject them elsewhere in your application. If that's all you're looking for, then this argument doesn't matter too much to you. So is Kodein stable? That's probably the very first thing that you should consider when using any application library. Kodein started in 2015 as a concept, and in version 2 is really when Kodein kind of figured out exactly what it wanted to be from an API standpoint. The switch from 2 to 4 had several minor changes. Some of them became kind of major. And then the last major change was from 4 to 5. So from 5 going forward, there's pretty much no changes in how you use the API. There was a lot of under the hood changes and feature improvements and things of that nature. But development has started to really slow down. And Kodein itself is, I forget the gentleman's name, but the developer has made kind of a business on the side off of Kodein, where he sells himself to help companies adopt it and use it. So this is great for the ongoing of Kodein, that it's actually making him money and paying for him to keep developing it. But he is also active on the Kotlin Slack if you go there and need help. And let's see. So does it do cool Kotlin things? Yes. The library is riddled with infix functions, reified inline functions, and all of that is combined to create a simple DSL for defining the modules, defining the Kodein instances, and performing the bindings in your code. So when you go to use it, it feels Kotlin. It's not a Java library that you're just using in Kotlin. It is a Kotlin first library. And hence from that previous list, you saw that it supports multi-platform projects. So inherently it must be pretty Kotlin focused. So how do you bind an object? This is going to be like the most simple binding. So here we can see that we bind a manager, and manager is just the type, with a singleton definition of a manager instance. Now this does not execute when the binding table is built or when the graph is built. So what will happen is the very first time that you call singleton, that is when the manager will be instantiated. Typically, that is what you as a developer want, and it does have a way around that using an eager singleton. However, it's something to consider with Kodein that it is lazy by default. So unless you want something not to be lazily loaded or deferred until you need it, you need to actually tell it that. Otherwise, it's doing what it would assume is the best thing, which is push it off until you absolutely need it. And that's great for memory management. It's great for speed of loading. And it's probably what you were looking for in the first place. Provider is going to be the next most common, maybe even more common than singleton. Providers are every time I want this injected, go ahead and build me a new instance. This can be really useful for memory management, where you lose that tight coupling, where a singleton will live forever. These provided instances, once you're done using it, GC can go in and clean it up and throw it all away. However, of course, that means that if you had multiple pieces of code that needed it and on the same screen at the same time, you might end up with more than one of them at the same time. Kodein does provide a solution around that called scopes, where you could do scoped singletons. And that would be like the middle ground of providing it only when it's needed, but keeping the same instance when you're inside a certain scope. It also supports tagging. A lot of cases come up when you are using dependency injection. The best example is probably strings. So you probably have at least one API that you talk to in your application. If you had 2, 3, 4 APIs, you probably want to make the strings injectable because you likely have dev environments, or even in production, you have your real production, and then you have your BVT testing production, and maybe other modifications that you need to make like that. And these string tagging identifiers make it easy to define which ones you want to use at any given time. And those work with all of the binding types. Factory, under the hood, a provider is really just a factory definition. It's just a no argument factory. So in the case that you need a provider, but with a input, a factory is what you're looking for. You can actually use multiple input factories. So if you needed multiple parameters, that is a possibility, but it's not really an ideal implementation. It would be preferable to have a more factory pattern where you produce a dependency that will then go do that for you rather than pushing it on a DI framework. So use these sparingly, they get confusing. And looking at some of the other ones, as I mentioned, it has eager. So if you would like the graph to instantiate an object when the graph is defined, that is an option. Multiton is an example of singleton instances that are bound to a specific type. So if you can think of a factory where you give it, in this example, an integer, every time you give it the integer 1, you will always get back the same instance from that Kodein graph. Instance binding is, I believe, like constant, but for complex objects. And then scoped is a way to use things like singleton, where they're only a singleton in a certain context. A great example of this is if you think of the activity lifecycle in Android, you can use scopes to bind to the activity lifecycle so that you have a singleton that lasts as long as that activity is alive, but then goes away when the activity is killed. Furthermore, you can use the scoping to pass down to things like your fragments and views so that they could share the same singleton instance or not. That's up to you, but you do have that flexibility. My word of advice, though, is to use that sparingly, because scoping becomes very difficult to understand from the developer perspective, and it puts a lot of onus on the developer to test things at runtime, which treads into the negatives of using a runtime dependency framework versus a compile time like Dagger. You can create instances where it's not going to work, and you're not going to find that out until the runtime. So try to be smart with those and try to be defensive in your programming if you're going to use them. So Kodein, one of the biggest features is the concept of having the Kodein graph and having Kodein modules. Modules are a great way to define dependencies that are reusable. So if you go back to the library concept, if you built a library and you wanted to make it easy to use with Kodein, you could write your own Kodein module that users could then import into their Kodein graphs. And now there's no more setup instruction past that. Like, they've done it. All they have to do is inject whatever the entry point is to your library, and everything should be good to go, right? And inside your own application, you often have dependencies that are highly related. You might have a manager, and the manager is the sole user of a certain database or HTTP connection. It's really great to define those together so that when you get to the runtime, you haven't missed any dependencies and you won't have any errors around a missing dependency. or dependencies that have been defined multiple times, which is another possibility. So to actually make a module useful, you do need to create Kodein instances, which I have a typo here. This should just be Kodein, not Kodein.module. But Kodeins can extend to other Kodeins, and Kodeins can import these modules. And a key thing here is that a Kodein instance is the complete graph, whereas a module is just a set of definitions. What that means is if a module was to define a singleton, and then you imported that into two separate Kodeins, you would have two separate singleton instances, because each graph is independent of each other, unless the graphs extend, in which case the bindings are all copied and singleton and multi-ton instances will be repeated between both of them, so you will get the same instances. And this is an example of what importing a module looks like. And modules can import other modules, and Kodein instances can import modules. So the syntax remains the same no matter which scope you're working inside of, which is, again, really helpful. And I left the comment there, again, about the singletons. So from a dependency retrieval side, we've covered the definition side pretty well. But how do you actually get it? Kodein objects, you can actually grab instances from directly. So if you had a Kodein instance, you can just call instance on it. This has changed a little bit as it's progressed to becoming lazy only. So now instead of equals, you would use by, and by would just permit the lazy loading. But this is generally how you would do it. And if you did need to use the equals for whatever reason, you can actually just do Kodein.direct.instance now, which would be the more correct. But to keep the slide small, I just left that out. And the direct Kodeins are actually just a Kodein instance. So if you needed to pass that around inside your application for whatever reason, that's not a problem either. So this would be a more typical instance. You would typically have some kind of class that's the entry point of your application. In this case, I just call it manager. It might be application for you, but you have your Kodein instance that you're defining. And by being Kodein aware, you are overriding the Kodein to use, and now all of your instances are available. So here we have the example of using the by, which permits the lazy loading. So the database will be injected on the first use case of that database. This is a more Android-centric example. So if you look at the application class of your Android application, this might be a typical implementation that you have. This is what it looked like for Kodein 4 with Kodein.lazy. With Kodein 5 and 6, you actually don't need the .lazy because, again, it's lazy by default. So you would just drop that, and now you have even less to type, so even easier. From an activity perspective, Kodein provides a lot of features around supporting Android. So you can take the approach of using a abstract activity instance that would set up all of the Kodein dependencies for you, or you can actually just use Kodein aware and inject the Kodein yourself. It doesn't matter, but it does give you the flexibility from a testing perspective. So I have a few samples that I created in IntelliJ. So let me switch over to that. Where did Jitsi go? There it is. Okay, so we have IntelliJ here. From getting started, if you were to build a Java application, this is likely what the application would look like. From an entry point, you would have an application class that represents the work your application really does, and you'd have an entry for export into the jar, right? So the function main is your entry point, application is the actual application, and then all this does is print a message. So if we walk through this, we've defined a Kodein instance. This Kodein defines a constant called message, and its value is hello world.
Hey, sorry, Ian, could you zoom in a bit?
Yeah, let's see here. Where's the...
I think you could just do the pinch if you're using the Mac.
Nope. Isn't there a...
Yeah, I think you go into like preferences, and then there's like a font, editor font option, so you can change it.
There should be a presentation mode shortcut.
Yeah, presentation mode's not too good. You said font? Just tell me when. Is that better?
Yep.
Okay, so in the application, we've overridden the Kodein instance here, and we can see that it's injected there. And we're using the message by grabbing the instance message, which is defined here. So when we call print message, we should get the value hello world, right? So if we just click run on this, it will run, and I can't make this text size bigger, but I promise you it says hello world. Okay, so that's a very simple example. And it obviously gets more complex from there. So from using modules, which is what any more complicated application is going to use, we can see that we have a module. Did it not copy? Wow. Okay, it doesn't copy over the font sizes. Does anybody know the hotkey for that? It's not control mouse wheel.
Maybe control plus.
Okay, and presenter mode only works. Any suggestions?
Doesn't the presenter mode work?
Yeah, but then it goes full screen, and I have an ultra wide, so it's probably not very helpful.
Oh.
We can do that though. Does that actually look okay?
Okay, yeah, I can see it on the stream.
Okay. So here we have two modules. We have first module and second module. And so you can imagine these being two separate logical dependencies inside your application, like maybe a manager's or two different databases. And each one is defining its own string, and these are tagged bindings, and each one's a provider. And so we're providing first for the first one and second for the second. And here in the Kodein instance, we're importing both modules. And again, in the application, we're going to inject the Kodein. And then because it's Kodein aware, we can just use by instance, and using the correct tag, we're going to get the correct strings. So if we look at what we have first and second. So that's going to print first, new line, and then second. So again, if we were to run that, we would just get first and second. So as expected, pretty simple. And if there is any questions, Ian, feel free to stop me, and we can go over those. So going to the next one. Should have named these with numbers. Oh, did I not? Oh, yep. Okay, let's see what I did here. So this is an example of inheriting Kodein. So very similar to the modules. Instead of passing modules around, we're passing around Codeins. And this is something you want to be very careful and considerate when doing. Generally, in application, you probably do not want more than one Kodein instance. However, there are going to be times where that is actually what you want. So if you can imagine a complicated app, there might be a lot of argument for having multiple Kodein instances just from a memory footprint perspective of how many dependencies you want in the graph and how many classes need to be loaded when the graph is created and how many dependencies you need in certain parts of the application, or possibly even the case of needing multiple instances of singletons that are isolated from each other, again, in the memory and have their own sets of dependencies. But before you go down that path, make sure you really understand it. And so I just wanted to provide this as an illustration of being very similar to the modules, but also understanding that it is different. So same thing, we have first, we have second, you extend them inside of this at coding, and then you can inject it there. So we should end up with the exact same result, which is just the first, second on the new lines, but it is functionally different. So going to the next one. This is okay. And what I'm going to show here is an example of when you extend Codeins, I mentioned that when you have a singleton definition and a coding, that any coding extending that coding will carry over its singleton value. So we've extended the coding here, and we're doing things a little bit differently just to show how you can do it. This is using the direct instance binding, like I mentioned before, which is effectively the same thing as using the by. We just skip the lazy. So here we're going to do a referential equality check. And so what we should see is that even though it's two separate codings, these singleton instances are the same. So if we run that, we should see true as the result, and we do. So that's really important to remember when you're extending versus importing. If you were to import, you could end up with two different instances of the same singleton, but you would need tagging to provide that. So like A and B, and it would be kind of, again, something probably to be very considerate about before you go down that path. From a debugging stance, Kodein, because it is at runtime, it actually has the entire graph available. So when you look at your modules and you look at your Kodein instances, sometimes it's really useful to be able to just print out what's in them. At the same time, if you were to look at from a debugging standpoint and run the debugger and break on the memory point, you could actually see the full Kodein graph if you were to dive into it. But it does have this helper where you call this not so convenient chain of methods, and you can print out the full description here. And so what we should see is a definition that defines our module and then provides and then shows this binding that's separate. And here we can see that we have our module is right here, and our binding is right here as well. Obviously, it doesn't have the actual value instances because we haven't asked for it to provide them yet. And same thing for the singleton. This hasn't been bound yet inside of the graph. So all it knows about it is the string types. And we can see all that reflected here is that we have the string provides a string, and a binding of any provides a string as well. So go to the next one. I mentioned earlier that Kodein provides the ability to override bindings. This is another red flag one of something that you definitely want to avoid because it gets confusing really quick. But in the cases where it's your only option, overriding is a possibility. So we have a module. This module is going to bind a string with the singleton value of module string. And in this case, we've decided that we've imported this, but we don't want this definition. We want to replace that definition with this definition. So if we were to run this, what we should expect to see is a printout of override string rather than module string, which we see here. So that is the way to do the overrides. And again, I would really recommend avoiding those whenever possible. It's been my experience that the times when this is most useful is when you're writing your unit tests. You may need to depend on Kodein instances or module instances to try to pump up your code coverage results. And in that process, it becomes really useful sometimes to be able to inject your own mock instances over the ones that were already defined inside of the modules or inside of the Kodein instances. And that's probably the most valid use case for using overrides versus in your actual runtime code where it would be potentially dangerous for you to do that. And I think, yep, we got two more examples. So as you're building apps, the very common need that you're going to run into is that you have dependencies, and those dependencies have their own dependencies. And the modules provide a really easy way to combine all of those logical dependencies together. But when you're defining the top level dependency, like your manager or your database, and it depends on some strings or other instances, what does that actually look like? So very similar to what we were doing earlier, we are binding a message writer with a provider of message writers. And this takes a message, but it also is injecting that message. So we don't know what it is yet, but we know that we need it, and we're telling Kodein that this needs to be injected. So from a dependency chain, we're going to go retrieve this first. We're going to use that retrieved binding to create a message writer, and then we're going to provide that instance. And we can see that the the value that we're going to inject isn't even defined in this module, which is the really empowering part of dependency injection frameworks, is that all of these can come from anywhere. And so we're going to import the module, and then we have the provided string that's going to be used to generate the writer. And following the code here, all the writer does is provide a way to print whatever that message was. So very similar to our original example in getting started. We're just going to print out hello world. So we can run that, and we see hello world as the actual print. And we see the inversion of control here, which is the more complete example compared to the others. And our last one, while you can use Kodein to help manually look inside of your graphs, what happens when you make a mistake? So here we have a module, and we import the module into a Kodein. And I've made a mistake here that my Kodein is importing my module, but it's also extending a Kodein that already imported the module. And again, if we think about a complicated application, this is a really common and easy thing to do where you have multiple definitions coming from the same place. So when you're developing, what would you expect to see? And here we can see a message that's telling us the module called module, which is the name here, has already been imported. And when we follow the arrow lines, it's going to take us to the second attempt to import, which is right here, and telling us that, like, hey, you can't do that, right? Now, inversely, what if the Kodein had been, I can't type in here. Let me just fix this real quick. So if the Kodein instance had been, what's going on? So I seemingly can't type in IntelliJ. Okay, so I don't know what's going on. Like, I can't type at all.
Maybe try the presentation mode, enter and exit it.
Yeah, maybe. It might be something to do with presenting to Jitsi. Okay, so if I were to invert that, where I extend second and import first, the error message will actually change to a warning that you can't override an existing dependency. And same thing, it'll take me to the line of the of what caused that, which would be the import on line 14. So sorry, I can't show you that error message, but that is what would happen. You'd get a very logical and reasonable error that most importantly takes you directly to the line of code that was the offender. And hopefully through that, you can see where some of the value of the runtime versus compile time that you have in Dagger is really actually nice from a developer experience, that you get these really helpful and useful error messages. And another part of that override message is in those cases where two things are defined the same thing and it's not an import, you'll actually get a printout of the graph. And you'll actually get that same graph printout if you were to do something like try to depend on a dependency that's not in the graph, which is another very common mistake to make, which is you're building some new code and you forget to import a module that you need as a dependency. If you were to do that, it will actually tell you that it couldn't find the binding. It'll tell you the binding that it was trying to look for in the error message. And then it shows you the graph of bindings that were available. And because the graphs are broken up by the modules, it usually becomes really easy to debug and go, oh, I just forgot the module. Or maybe you were meaning to add a specific binding definition and you just forgot to add that. So very, very helpful from a development perspective to have those features. Let's see. Cool. So I think that's pretty much it for me. I do have a old samples repository that I believe was for Kodein 4 that I didn't have a chance to update for this. The code that I showed here isn't in a repository. It's just a couple like random classes in a project. But if you wanted to see more examples, you can check out there. I'm Toxic Bakery on pretty much any social media that you can find that I'm actually on. So if you wanted to reach out to me, that would be the way to do it. And that's it, unless anybody has any questions.
Thanks, Ian. I have a question regarding scopes. And how do you manage them? Like, you just assign a key and then like recycle that key, or?
Yeah, it's a great question. Scopes are kind of complicated. I wanted to show a demo of it, but there's just not really a good way to do that concisely. It would be a lot of walkthrough, but the general idea is, if you can imagine the life cycle, such as like Androids, you have an onCreate and you have an onDestroy. So what a scope does is, through some binding code that you would define as a scope lifecycle, you can create scopes that will automatically bind to those onCreate and onDestroy events. And through that, they can recycle parts of your graph. So it can go through the graph and know that everything that was attached to this scope should be destroyed or should go through the creation process. So when you look at the binding side, you would just bind with that scope, right? Well, the dependency retrieval side, rather. So you would just say that bind by scope, and then provide it, such as like maybe your application context or your activity as the scope, and that would allow the automatic calling of that binding lifecycle, and it would handle all the dependencies for you. So from a DSL level, it is very convenient to use, but it does require doing that work on the back end. And Kodein does provide Android lifecycle bindings for, I believe, activity fragments and views. Maybe not views, but definitely fragments and activities. So if you do want that, they do have features for it. Again, it would just be my recommendation to be very hostile to the idea of bringing them in, because it does add a lot of mental overhead, which is not necessarily helpful unless you have a very strong argument for using it. I can tell you that our production application, I believe, is around like 40,000 lines of code now. We probably have a few hundred dependencies defined in Kodein, and our startup time is not an issue because of the lazy loading. And we do not use the scopes, and we have not had issues with that. So you need to be in very particular situations where it becomes a necessity.
No, thank you. Yeah, it seems way nicer than Dagger, especially those error messages.
Yeah, the error messages are fantastic. I would start there as probably the solid argument of why you would want to use it. That and using the modules is just so easy. There's almost no learning there compared to the Dagger guide, which we've all cried trying to read through. I think I did. I don't know if other people did.
Oh yeah, I dream about that thermosifan.
Yep, whatever that is. I have a Keurig. I hit the button. So all of everything in that guide is Greek to me.
Okay, well, thank you for the talk, and thank you, Filip, too.
Thank you.
And see you maybe next time or another time.
Yeah.
Awesome.
Thank you for having me.
Thank you.
Bye, guys, and
Bye.
bye everyone watching.